Okay, good. So welcome back. So we now have the part 2 of Geoff Penington's set of lectures. Thank you.
Okay. Okay, cool. So this lecture we're gonna switch tack somewhat from last time, and we're not going to talk about black holes or their information content. Well, we will in the context of ADS-CFT, but we're going to be focused on a set of ideas in ADS-CFT that started with a famous paper by Ryo and Takinagi in, I think, 2007, possibly 2006, I forget, sometime around then, and a load of generalizations that have happened since. And all of these ideas are about how to compute entanglement entropies in a holographic CFT using the bulk quantum gravity description, okay? So this circle is a brilliant artistic rendering of our CFT, which we're imagining is on some sphere, or for CFT2, ADS3, it's a circle across time, okay? And the Hilbert space sits on this circle, and heuristically, we can think of this Hilbert space as factoring into a tensor product of local Hilbert spaces at each point. If we regularized on a lattice, say, that's what we'd have. Formally, for the actual CFT Hilbert space, you can't really do that, but as physicists, we pretend you can, and it basically makes sense. And then we can consider some sub-region of the boundaries. So maybe in this CFT2 ADS3 example, we consider some region. It's a bit useless. Let's try blue. Some region here. Maybe a bit over here as well. Okay, and this is the region B, and we want to compute the entanglement entropy S of B. So Ryo and Takinagi answered this question in the context of static states in the bulk, also static on the boundary, I guess, in the limit where the gravitational coupling G goes to 0. Okay, this is the large N limit of the holographic CFT. And they argued that this entanglement entropy is going to be given by the minimum over all surfaces gamma of the area of the surface gamma over 4G plus a correction that's meant to be of size order 1. Okay, so this is the leading order term in an expansion in G. Okay, so what is this surface gamma? It's not just completely any surface. It has to satisfy something called the homology constraint, which says if we take the union of gamma together with our boundary region, big B, that itself should be the boundary of some bulk region, little b. And the other thing is that we're considering a static state, so all of this should lie inside the static slice that contains the region big B. Okay, so roughly speaking, this just means that the surface gamma has to be anchored on the boundary of big B. So for example, in this case, we could consider a couple of different possible surfaces. You could imagine a surface that's one component over here like this, and another surface component over here. Okay, that's sort of roughly what the smallest area surface anchored on big B would look like with that topology. There's also another topology that we could have that has a smallest area surface that looks like this and this. Okay, so those are two possible candidates, either the union of these two more vertical lines or these two more horizontal ones for the Ryo-Takinagi surface, and in general it will just be whichever one of those, in this case, is smaller. Okay. Okay, so I said it's roughly speaking that, it's not quite that. So we have to be a bit more careful if, for example, we have a two-sided black hole with two boundaries over here. Sorry? Yeah. Okay, so then we have a wormhole connecting the two of them. Okay, and we can consider the entanglement entropy of the entire left boundary with the entire right boundary. Okay, so in this case, there's no boundary to our boundary region, right, because it's an entire component of the boundary. And so you might think the smallest area surface that has the same boundary as that is just the empty surface with 0 area. But that wouldn't satisfy the homology constraint because big B itself, in this case, is not the boundary of some bulk region, right? If we try to have it be the boundary of the entire bulk, that's not only this end of the wormhole, but there's also this end of the wormhole. Okay? In contrast, with something like vacuum ADS, then if we took the entire boundary to be our region, we tried to compute the entropy of the entire boundary, then that is the boundary of the entire bulk, because we only have one boundary. Okay, so in fact, in this case, the RT surface will be sort of the narrowest neck of the horizon. It will basically be the bifurcation surface of the black hole. And that's actually, yeah, that's the smallest area surface that satisfies this homology constraint. So in this case, the union of this asymptotic boundary and this horizon is the boundary of the bulk region consisting of the left wedge of the black hole. Okay? Great. So one other thing that deserves to be mentioned about this formula is that neither side of it make any sense at all mathematically. Okay? So entanglement entropy in quantum field theories is famously infinite for any local region, any region with a boundary. And that's just because of our computation yesterday, where for windless space, if we just zoom in locally to a point here, then everything just becomes like windless space. The state looks thermal, and we have an infinite number of Windler modes, an infinite number of simple harmonic oscillators, all of which give a finite contribution to the entanglement entropy, and so you end up with some infinite answer. Okay, so this is infinite, but fortunately, this is also infinite, actually for a couple of reasons. But the important one that matches this infinity is the fact that the area of these surfaces diverges as we go out very, very close to the boundary. Okay, that's how ADS works. We draw it as this compact space, but really the metric diverges near the boundary, and so it's an infinitely large volume. Okay, and those two divergences are identified. So this one is an IR divergence in the bulk theory. It's about large volume effects. This one is a UV divergence in the boundary theory. It's about very short distance effects. So that's actually an example of what's called the UV-IR correspondence in quantum gravity, that highly UV things in gravity can end up being related to highly IR things. Okay. Great, so this is obviously a very cool formula, but it's not super general. It's just giving us the leading order piece, and it's just telling us what to do for static states. So we'd like something more general. Okay, so there's two ways we'd like to generalize this. The first is to allow sort of general time-dependent states, time-dependent bulk geometries. This was done first by some people called HRT, Cuban, Rangmani, Takinagi, and then later there's an equivalent formulation due to Wall, which is in some ways nicer, arguably. Certainly is aesthetically nicer. And we'd also want to understand these order 1 corrections, which really come from quantum effects in the bulk. So this was done first approximately by Faulkner, Lukowitz, and Maldacena, and then later, the full right answer was obtained by Engelhardt and Wall. Okay, so how do these things work? Let's first do the time-dependent case. So that tells us the Wall version, which is actually the later version, says, okay, in the static slice, we knew which Cauchy slice we should be looking at when we find this minimal area surface, right? But when we have a time-dependent space-time, clearly it doesn't make sense to look for the minima over sort of all possible Cauchy slices. So here we have a full space-time, the can of soup of ADS, because you can imagine some really weird Cauchy slice that sort of entirely consists of light-like pieces zigging backwards and forwards in time. I'm not going to try to draw that on here because I don't have the aesthetic talent, but you can make it so that everything is light-like, and in fact, the minimal area surface, if I just allow the surface to be in any Cauchy slice, then I can always find a 0 area surface homologous to any roundy region just by having it go along light-like pieces and then backwards along light-like pieces and so on. Okay, so we need some other condition to pick out what the right Cauchy slice is in which this thing's meant to be minimal. And Wall's answer was you just first look in all possible Cauchy slices, you look for the minimum gamma in C, satisfying the homology constraint as before, of area gamma over 4G. And then once you've computed that for all possible Cauchy slices, all you do is look for the Cauchy slice that gives the largest answer here. Okay, so this is called the maximin prescription for holographic entanglement entropy. So we first minimize within a Cauchy slice and then maximize that minimum. Turns out that there's an equivalent description to this, which is actually the one that was first developed by Humani, Rangmani, and Takinagi. That's sort of simpler to do in practice. And it says, so it's still plus order 1, it says instead of using this minning over within C and then maxing over C, you just first look for all possible surfaces, gamma, that are extremum of area. Okay? So all that means is that any linear perturbation in any direction does not change the area. They're critical points of the area functional on the space of surfaces gamma. That's some horrible infinite dimensional space, but you can still define that well. Okay? So in general, there can be a whole set of these things, but it's a discrete set. And then we just minimize over the elements of the set. Okay? So that's the sort of extremal surface version of the formula. And now we're almost done. The only remaining thing we need to do is say what these order 1 corrections are. And they're actually pretty simple. Turns out they're just given by the entanglement entropy in the bulk. So in the bulk, we have quantum fields, we have matter fields. In principle, we have gravitons that we don't know how to treat very well, but we pretend we do. But in particular, we have matter fields, and those have some entanglement entropy for any region. And we're just going to add the bulk entanglement entropy of the region B, okay, where B is defined uniquely by the fact, it's just a unique region that is bounded by big B in our surface gamma. Okay? So an obvious complaint at this point is that this thing is again infinite. So we've added an order 1 correction that is infinite. Fortunately, even though I said this was infinite, but we dealt with it, that was about the area being infinite. We also need to take into account the fact that in the denominator, G is infinite. Okay, and G is infinite just because we need to renormalize our theory. And so our bare gravitational coupling needs to be infinite in order to have the low energy effective theory be described by a finite coupling description. Okay, so over here, where we're ignoring the order 1 corrections, then we should think of this as being the sort of renormalized low energy G. Okay, and so this does make sense as a formula if we sort of imagine that we've integrated out all the fields and so on, and we just have some low energy description that has some finite G. But now that we're including those fields, then this is the bare gravitational G. And in fact, so that includes some counter term. It's therefore infinite. But this sum is supposed to still be finite. And in general, it will differ from having the renormalized G here by just some actual order 1 term. The other way to think about it is think of this as being defined with the renormalized G, and this being some sort of renormalized entanglement entropy, but I think that's actually less clean. So the right thing to do is think of each of these terms as individually infinite, but they add up to some finite piece. This full sum, by the way, is known as the generalized entropy, or SGen, of the region B. Okay. Any questions about all of that so far? Yep.
So I've often said those words that SGen is supposed to be some UV finite quantity, and
Yep.
Engelhardt will have some argument for it, but is there like a quick and easy argument for... I never particularly understood why it should be true.
Yeah. Okay, so the leading divergence in the bulk entanglement entropy is just proportional to the area of the boundary of the region. This is just because it comes from local entanglement of Windler modes just across the surface, and the number of such modes. You have transverse momenta or equivalently transverse positions describing all those modes, so it scales as area. And G has some renormalization, so you get some polynomial divergence in the cutoff scale, but we have area on the top. So sorry, by units, the leading divergence in G has to be order 1 over epsilon to the d minus 2, okay, where epsilon is some cutoff length scale that's going to 0. And so if you take this is you take it as G renormalized plus this, the bare one. Okay, this is the leading order divergence, and then plug that into there. Pretend this term is small, and you'll get the same divergence of area over. You get a divergence that looks like area over epsilon to the d minus 2 minus that. Okay, so that exactly cancels the divergence of area over the length scale d minus 2 from the bulk entanglement entropy. There are other divergences to the bulk entanglement entropy that are subleading. There is, it has not been checked order by order for all of them that those divergences actually cancel and this is well defined. There is a sort of higher order, more general reason to think that they have to. That comes from how we're going to derive this thing, which we're going to do later in the lecture. So hopefully I will remember to comment on why that derivation suggests that all these divergences cancel out. But if I don't, then shout at the end. Thanks.
Okay. Can I speak? You have to ask you if you could clarify what is S bulk B small b, and maybe draw small b.
Yeah,
and the second,
okay. So let's say this is gamma, and this is gamma. This is B. Then little b is everything between big B and gamma. Okay? So it's defined by this condition that they're always, gamma and big B together have to be the boundary of some region.
And the two-sided that yes black hole?
Yeah, so for the two-sided case, we have gamma here, we have big B out here, little b is just the stuff in between them, so it's the entire left exterior of the black hole.
And S bulk, how is it defined?
Yeah, so then S bulk is so in the bulk, we have bulk quantum fields. Yeah. Okay, in quantum field theory, the same way that we can define an entanglement entropy for a boundary region, big B, because that's some quantum field theory, we can define an entanglement entropy for the bulk quantum field theory on the region B.
Okay, and if you could clarify, I want to ask you if you could clarify the relation between max-min and minimum of extremal.
Yeah.
That's something that I lost, maybe.
Yeah, so this is a non-trivial equivalence. So these are two possible, seemingly different prescriptions. So one of them, we take this quantity, we minimize it, we pick some Cauchy slice, we take this quantity, we minimize it over all surfaces within the Cauchy slice, then we maximize over all possible Cauchy slices. Okay? This is a priori totally different procedure that turns out to be equivalent. It's a non-trivial proof. You can read Aaron Wall's paper, but I'm not going to explain it to you, where we instead just look for all surfaces in the entire bulk, okay? And we look for ones that are local extremum of this quantity, i.e. that means that if we perturb them a little bit, then there's no linear order change in this generalized entropy quantity, okay? And that gives us some discrete set of surfaces, and then out of that discrete set, we just pick the one that has the smallest generalized entropy, okay?
But it's not evident that the two things are equivalent.
It is not, it should not be obvious to you that the two are equivalent. I'm claiming they are. I'm not going to give the proof because it's
Thank you very much.
Okay.
Sorry.
Yep.
So two things. One, just to clarify notation. On the left board, you have infinite pointing to a quantity. And on the right one, infinite pointing to the same quantity. On the left, the whole expression is infinite because g goes to 0. And on the right, g goes to infinity.
No, we're taking g to be small but finite. I'm ignoring the fact that g is going to 0 and so these are power series.
Yeah.
Even at finite g, where we have, but small, where we have order 1 corrections, but they're subleading, then the area on the top is infinite, okay? And this entanglement entropy is still infinite because even at finite n, we have divergent entanglement entropy, okay? Then over this side, we have two more infinities that, again, are not involving like n to infinity, right? So n is telling you what the renormalized g is. That's the identification there. So that's the thing we want to be finite. But now in this formula, unlike in this formula, we want this g to really be the bare gravitational coupling, which is still infinite. Okay, so that gives another infinite divergence. This time, that one does not contribute to a divergence over here because it's cancelled out by an infinite divergence from this one.
Cool. And is that, does that receive order G corrections?
Yeah, there'll be, yes. This will have order G corrections. In fact, the trouble is once you go to order G corrections, then you start having fluctuations in the geometry, and these things get very hard to define, and generally it gets a lot more messy.
Sorry,
so I don't think this statement is even really defined. In fact, I think really if you want this statement to be well-defined, you want to be taking a limit where the contributions from this thing are larger than order 1. Say you have a large number of bulk fields or something, so that they're larger than the contributions from fluctuations in the geometry. So that's if you really want it to be controlled, but heuristically this is... I expect there is a version of this, if you define your terms precisely enough, that should be true to all orders in G, up to non-perturbative corrections, but it would require a lot more work to define. Like the right statement would be, this is going to come from saddle point approximation. In principle, if you expand about the saddle point to all orders, include all perturbative corrections, then that should give you a correct answer up to non-perturbative things. But we're sort of not being careful about enough by what we mean by this to really be taking those into account.
Cool, thanks.
Great. Okay.
Sorry, just
Yep.
so when you have still G being the renormalizable G, how do you even define the minimum if all your quantities are infinite?
You mean because this area is infinite?
Yeah, so before when you were still dealing with the renormalizable
Yeah,
G.
great question. So the answer is that the infinite part is universal. So the difference between any two areas is finite.
Okay.
So you say the difference between these two and these two is finite because all the divergences come
From the boundary.
So that's actually, if this quantity is infinite and we're saying infinite equals infinite, like what does that even mean? That's just trivially, vacuously true. Okay, the meaningful part of this statement is I can take combinations of entropies that will be finite. So for example, I could take the mutual information between two different regions that are separated from one another. That will be a finite quantity in quantum field theory. It can be defined rigorously with a load of work. The area divergences will cancel, and so you'll get a finite quantity in the right as well. Great. Yep.
Yeah, sorry, just to clarify. So, so the entropy of your time-dependent scenario, that's still infinite, but you only want that to come from the area, like divergence, not from the G or the S.
Yes, exactly. So it's the IR area divergence that comes from going out near the boundary that's actually going to give us the divergence in this thing. Technically, there's also an IR divergence in this bulk entanglement entry that will also contribute to it in a subleading way. But there's also UV divergences in each of these two things that come from the renormalization of G and the UV entanglement of modes very close to the horizon. And those cancel out with one another, and they do not give an infinite contribution to this thing.
Okay, thank you.
Yep.
Yeah, I'm sorry, one more clarification about that. So it seems like you have this UV divergence coming from the fact that G just runs to infinity, but then you also have a purely QFT UV divergence of the bulk entropy. So do you have to tune some parameter to make that happen, or they just cancel each other for some other reason?
So it's pretty obvious that the leading order things cancel each other. That's the argument I gave here. There is a deeper reason why they should cancel each other that we'll get to later.
Okay, thank you.
Yeah. Okay, great. So there's one remaining thing which I should talk about very briefly, though it's mainly going to be the focus of Chris's lectures later this week, and that's this idea of entanglement wedge reconstruction. Okay, and so what does entanglement wedge reconstruction say? So let's say we have some boundary region big B, and it has some surface gamma, and there's a region little b. that lies between gamma and big B, as usual. Then entanglement wedge reconstruction says, roughly speaking, that the state of the boundary on big B describes the bulk state on little b. This is sometimes called subregion duality. It says that the region here is holographically dual to this region here, just consisting of little b. Okay? And there's a lot you can say about how to make this precise. It involves ideas from quantum error correction and so on. I'm just going to give a very simple, low-level argument for why we should expect this to be true, just from these formulas here, which is, let's just imagine we have some simple system like a qubit, just a spin, sitting somewhere in this region, little b. Okay? Now we can imagine that this qubit is entangled with some reference system over here, okay, that's outside of the bulk. It's just maximally entangled in some bell pair state, okay? And then we can compute the entanglement between just this boundary system, big B, and this reference system R, okay? And if we find that they're sort of maximally entangled, then we'll conclude from that this qubit here is encoded in this system here in exactly the same way that we did last lecture with the Hayden-Preskel diary being thrown into the black hole, and then the thing that we was entangled with ends up entangled with the Hawking radiation. Okay? So let's compute these things. It's pretty simple to do. S of big B is just going to be given by some area over 4G that we don't really care about, plus the bulk entropy of little b, which includes, I'll call this little r, okay? So the bulk entropy of everything in little b, including this maximally mixed qubit in little r, okay? I've just sort of separated out the degree of freedom describing this qubit, okay? What about the entropy of big B and R? Well, that's given by an almost identical formula, except that we have to include R as part of our bulk entropy in big B. Okay, so now, rather than being A over 4G plus S of little b and R, it's S of little b, little r, and this extra external qubit in big R. Okay? But little r is maximally entangled with big R, so that means the entropy of this thing is 2 qubits smaller than the entropy of this thing. And so since these terms are the same, then this entropy is 2 qubits smaller than this entropy. Okay, so we conclude that this qubit in big R is maximally entangled, so it's maximally entangled with big B, and hence that the qubit little r that was sitting in little b is maximally entangled with big B. Okay, what about in the other case? Let's say R has now moved, so now R is sitting somewhere over here that is outside of little b. Okay, in that case, little r is no longer included in that formula there. It's also no longer included in this formula here. And so now big R is unentangled with little b. Okay, so it increases the entropy of little b and R is 1 bigger than the entropy of just little b on its own, because there's this one extra qubit that's just in a mixed state. Okay, and so that means the entropy of big B and big R is 1 larger than the entropy of big B. We conclude that big B is unentangled with big R. It knows nothing about the entanglement between big R and little r. Okay? So we conclude that big B encodes, it knows about this qubit little r, if and only if that qubit is contained in little b. Okay? Chris will give much general and more powerful characterizations of what entanglement wedge reconstruction really means later on, but that's a very surface level argument. Okay. So I've now stated all the basic facts of RT and its generalizations, but what we still want to know is why on earth is any of this true? And mostly, for the rest of the lecture, I'm just gonna derive this for you and do this beautiful derivation by Lukovitz and Maldacena, we'll just see that it's true. But I do want to give one nice piece of evidence first, which is checking, it's a sanity check that this formula is consistent. Okay? And that's the entropies on the boundary theory need to obey this inequality we saw yesterday of strong stat additivity, that for any three systems, A, B, and C, then we have S of AB plus S of BC is S of B plus S of A, B, and C. Okay? So our formulas for entanglement entropy that use the bulk damn well better satisfy that inequality, or we're really, really in trouble, right? They just can't possibly be true. Okay? Fortunately, they do, and it's a very beautiful geometric proof. I'm just going to do the version for the original RT, so static slices, and just including classical pieces, but the same spirit of the proof goes through. It's much more general. So we're going to have three regions, A, B, and C. I've put them next to each other, but they don't need to be. It just makes the drawings a bit simpler. And S of AB is computed by the minimal area surface going like this, homologous to AB. Okay? So this gives S of AB. We have another surface here. It's a minimal surface going around like that gives S of BC. Okay? And we want to show that the sum of those two surfaces has an area greater than or equal to S of B, which is the minimal area surface homologous to B, plus the minimal area surface homologous to ABC. Okay? This will take me exactly 2 lines of chalk. So all I'm going to do is I'm going to split up the sum of those two surfaces in a different way. I'm going to split it up into a triangle at the bottom down here that is homologous to the boundary region big B, together with this part and this part that is homologous to ABC. Okay? So that's just a redistribution of the two surfaces, so I haven't changed the area by doing that. But now I have a surface that's homologous to B, which necessarily must be bigger than the minimal area surface homologous to B, so it must be bigger than S of B. And I have a surface homologous to ABC, which must be bigger than the minimal area one homologous to ABC. So we're done, because that's what we were trying to show. Okay, so it's a beautiful, simple geometric proof that strong subadditivity is valid for the leading order piece in static spacetimes. As I say, the argument is more general, but it gets a bit more complicated because these surfaces can be in different Cauchy slices, and you have to use focusing arguments, basically mind blank on the word, focusing theorem, Rachel-Dory's equation, there we go, and its quantum generalization in order to take the surfaces that lie in different Cauchy slices and put them all into the same Cauchy slice. From there, the argument works in exactly the same way. Great. So, let's see, what am I going to get rid of? Okay. So I'm now going to start trying to give the Lukovitz-Maldacena derivation of all these formulas. And I'm going to be a bit more general than they originally were, because I want to get the quantum corrections, because the quantum corrections are fairly key, and they'll particularly be important tomorrow when we talk about black holes. But I'm not going to be completely fully general, because I'm going to assume that all states involved can be prepared by a Euclidean path integral. Okay, so just like we prepared the vacuum state yesterday by just having an infinite Euclidean path integral, then we can prepare other states in the same way by basically having a path integral, but maybe now we include some sources turned on at various points in Euclidean time. Maybe we have different geometries involved and so on. So this is a fairly general prescription. It's not just talking about the vacuum or something like that. But it's not completely general because the slices you get in this way, the states you get, always lie on a moment of time symmetry in the Lorentzian direction, right? Just because we haven't broken the symmetry between I and minus I yet. Okay? And that means that we don't actually need this maximization over slices. It's just we're going to directly get just a minimum area surface within some slice. Okay? So to deal with full Lorentzian geometries is pretty simple. You just have to have some Lorentzian path integral as well. Then you can basically prepare any semi-classical state you want. The trouble with that is that then the bulk geometries are going to become complex, and it's very, very hard to draw pictures that you guys will be able to understand. But trust me that it really is just a question of allowing some parameters to be complex, and otherwise the arguments go through completely unchanged. So I'm not like cheating here too much. I'm just trying to make it pictorially easier to communicate. Okay. So we have some state, psi, that's prepared by some Euclidean path integral. Maybe there's some sources down here, some insertions or whatever, but I'll mostly forget about those. Maybe it's just a vacuum state. And we want to compute the entropy of the reduced density matrix on B. Okay? So this seems a bit hard. It's sort of not obvious how to do it, because this is equal to minus the trace of rho B log rho B. It's not obvious, at least to me, a priori, how you compute that using something like a path integral, which is how we know to prepare these states, so how we know to do stuff. Okay? But there's a nice trick called the replica trick, which is just to observe that this is equal to minus the derivative with respect to n of trace of the reduced density matrix on B to the power n. Okay? It's going to turn out that at least for n integer, this thing is going to be relatively easy to compute. Okay? We're going to be able to do it using a path integral. And then once we know what it looks like for all values of n, we can hope that we'll get some analytic function in n, and then we can analytically continue to the limit n goes to 1, take a derivative, and have the entropy pop out. Okay? So that's the argument. There's some slightly dodgy maths there, but, we'll roll with it. Okay. So how do we compute this using a path integral? Well, the first thing we need to do is how to compute rho B using a path integral. Okay? So I told you how to do that yesterday, right? So let's take my other colored chalk. Let's say we have some region B that consists of a bit over here and a bit over here. Okay? If we want to construct the reduced density matrix on rho B, what we do is we have our ket path integral, we have our bra path integral, and then we partial trace, which just means, so we have the bra, we have the ket, we have the bra, and the partial trace means that we erase the boundary between the bra and the ket and just integrate over the fields on it everywhere outside of B. Okay? So in this case, previously the state was prepared by a Euclidean path integral on a hemisphere with maybe a couple of operator insertions. I think I'll keep these in. And we have the same operator insertions up here. Now, to get the density matrix, we have a path integral on the entire sphere, except there's a cut. There's a cut at the region B, so that the region B fields on the top hemisphere are not necessarily the same as the region B fields on the bottom hemisphere. Okay? That gives us basically a matrix on the space of fields on B, and that is the density matrix on B. Okay? Any questions about that? Because this is an important point to get right, and it's not necessarily obvious if you haven't seen it before. Yep. Yep. So, okay, I'll just say it once more time for luck. So the formula for rho B is equal to the trace over B bar of ket psi, bra psi. Okay? So the state bra psi, ket psi is prepared by this path integral on the bottom. Okay, that describes the wave functional of the fields everywhere on the sphere, everywhere on the circle, at the equator. The state bra psi is prepared by a path integral over the top half. Okay, and that's also a wave functional on all the fields on the equator. Okay, so at this point, the two hemispheres are completely detached. But then, when we do the partial trace over B bar, that means we take all the fields that are in B bar that are not in the region B. We demand that they're equal to each other on the top hemisphere and the bottom hemisphere. Okay, because that's what a trace does. We have a sum over a complete basis of states, and then we put a ket at the beginning and a ket at the end and a bra at the beginning. And so the full effect of that, we set the fields above and below the equator equal, integrate over those fields. That's just the same thing as if we didn't have any boundary there at all, and we'd just done a path integral over that whole region without any discontinuity of the equator. Okay? Great. But we still have this discontinuity on the region B because we haven't done any partial trace over that. So the fields there, we have fields on the top and fields at the bottom that come from this ket and the bra, and they describe the density matrix of the region big B. Okay. So now, we want to take trace of rho B to the n. Okay? So let me try and really draw this out very explicitly. Unfortunately, the limitations of my artistic abilities are going to strongly come into play here. I think it's important to really do this step by step. Okay, so we have now n copies of rho B. Okay, so let's draw them out. And then I had some field insertions at top and bottom. And then I have discontinuities here at the region B. Okay, and then I'll have another one. My drawings are going to get increasingly lazy. So we have n of these things. And each one, we have these same discontinuities. And then we want to take trace of rho B to the n. Okay? So then what does that mean? We take the first rho B, and then we take its product with the second rho B. So this means we should take these fields on the blue discontinuity here and glue them to the fields over here on the green discontinuity. Right? It's exactly the same reason when we took a trace over B bar, we glued these things together. But now we're taking the rho B, the ket here, and we're gluing it to the bra in the next copy of rho B. So the blue ket gets glued to the green bra. Okay? Similarly, the blue fields here get glued to the green fields up here. Okay, so that's the next product in the cycle. We have n of these products, and then eventually we take the trace, and that just means the leftmost one gets glued back to the first one at the beginning. So we glue these blue fields to the green fields all the way back here. Okay? So now we just have one big path integral, has no boundary conditions for fields anywhere because everything got glued to everything else, and that's going to compute this complex number, or real number in fact, that is trace of rho to the n. Okay? Is that clear to people? It again takes a bit of time getting used to, but it's worth spending a moment on it. Yep.
What are you trying to indicate by how you've drawn the top and bottom hemispheres?
Yeah, so when we just had rho B here, okay, we integrated over everything except for on this blue lines and on this green lines where we fixed the field configuration to be something in particular, right? So we had maybe phi of x here on the blue one, and then on the green one we had like phi prime of x. Okay? And so that gave us a matrix, an infinite dimensional matrix on the space of field configurations phi and phi prime. Okay? That is our density matrix. These are the columns of the density matrix. These are the rows of the density matrix. Or the other way around. I forget how matrix multiplication works. Okay? But when you then come to multiply matrices, what you do is, okay, let's try and write down matrix multiplication. So rho squared ij is equal to a sum over k of rho ik, rho kj. Okay? So that means you fix the column of this one to be equal to the row of this one, right? That means we fix the field configurations on this blue surface, on this one, to be equal to the field configurations on the green surface of this one. Okay? And then we sum over k. That just means we integrate over all field configurations. Now we've set these things equal and then integrated over the possible values. That's just like we literally glued these things together on the manifold and then just did a full path integral over everything on that without anything special about the surface here or the surface here. Okay?
Thank you.
And then we just keep doing that and we get this cyclic trace. Awesome. I really appreciate the questions because it makes me slow down and explain things better. So keep them coming. This is I really want to spend time over this derivation because it's a really beautiful argument, but it takes some time to get your head around. Okay. So this is some complicated geometry on n copies of the sphere or whatever it might be, n times as many copies as we had before. But it has a nice symmetry. Okay? It has a symmetry where we take this sphere, move it over to where this one was, take this one, move it over to where this one was, and take this one back to the beginning. Okay, if I do that thing, shift them all around in a cycle, then all the gluings are the same, all the spheres look the same because they all came from the same row, and so the full path integral is just the same thing. Okay? So we can do that as many times as we want. So this gives us a Zn symmetry that's related to cyclically permuting the n copies of our system. Okay? That's going to allow us, let's go over here. That's going to allow us to write this very complicated path integral on n different spheres in a much simpler way, as follows. We're just going to draw one sphere, okay? That again, it has the operator insertions or whatever we use to prepare the state. And this single sphere is meant to represent the quotient of these n spheres by the Zn symmetry. Okay? So we've identified this point with this point with this point all around the cyclic Zn symmetry. Okay? And the only new weird thing we have here is that we basically have a branch cut where B was. And what this branch cut tells us is just some, there's significant points here, and then I've drawn a dotted line here to just represent that's the side that matters. It says that if we start on what I call sheet 1, so the first sphere, okay, and then we go up here, but then back down through the branch cut and end back where we started, but we went through the branch cut once as we did so. Then when we started on the first sheet, we're going to end up on the second sheet. If we started on the second sheet, we're going to end up on the third sheet, and so on. Okay? Yeah, do you want
to? Excuse me, sorry, I'm a bit lost. On the drawing, isn't the first line that is coming should start from the right-hand side of the sphere and go to the...
I just drew 2 regions to make it more representative. But each of these lines, you should imagine happening on both sides because they're all just in the region B. B can consist of as many components as we want. Right, I've just drawn it as consisting of 2 regions to indicate that, but maybe we have a third region here, and that would also have a branch cut. Just whatever B consists of, then there's a branch cut that takes up the whole of big B. Okay, so all of those blue lines, all of the blue lines on here get glued to the corresponding green lines on this one. all of the blue ones here get glued to the corresponding green ones there, and so on, all the way around the cycle.
Yeah, so isn't it like the first one start from the right and go to the, go to, okay.
So this part gets glued to this part gets glued to this part. They both, I didn't draw arrows for both of them, but they both happen.
Exactly,
All the different pieces get glued to the corresponding bright greens.
Thank
so
you.
everything here has got glued to something. I haven't drawn, I don't want to draw too many arrows, but it's all got glued together.
Yeah.
Okay?
Thank you.
One question, can you confirm you're gluing just the CFTs, right?
Sorry, say this again.
Are you gluing just the CFT? So basically the spaces where the CFTs live.
So yeah, we're integrating over the field configurations of the CFTs.
Yeah.
Okay? But that corresponds to just doing a path integral on a space where we've glued the spaces together.
Yeah, thank you.
So the spaces are getting glued together because the spaces represent the space we're doing the path integral over, and we're gluing the path integral together.
Okay, thank you.
Okay? Great. Okay. So we're getting some progress here. So we've just represented this as a path integral over n copies of our whatever we use to construct the state rho, but we can just represent it by one copy with some branch cut that tells us if we go on a loop round, then we've actually ended up on another copy. Okay, this should be thought of as purely a notational thing to get us to not have to keep drawing out those n copies, because that's really, really annoying. Okay? Okay. So now we're going to try and compute this thing. Okay, so we want to compute trace of rho b to the n. And I said that that's just given by this path integral, which I could call Zn. Path integral on the n-fold cover of this thing with a branch cut given by that. But I do have to be a bit careful because this path integral on only one copy produces a density matrix, but it's not necessarily a normalized density matrix, right? Because in general, a path integral does not produce a normalized state. So we should divide through by trace of rho b to the n to make sure everything is normalized. Okay, I'm assuming rho b is normalized, but z is not. So that just means we need to divide through by the path integral on just one copy of this thing to the power n. Okay, so we need to normalize each of the density matrices. Okay, so that is, we've now set up the computation in a form that we can hope to do. And the idea is that we're going to compute this using gravity. Okay, so we've now, up until now, everything has been defined in the CFT, but this is in general some very hard computation in the CFT. There's some partition function with a strongly coupled CFT that we don't know how to compute. So we're going to use the ADS CFT duality. And a precise statement of the ADS CFT duality says that ZCFT, the partition function of the CFT on some fixed background with some sort of, maybe some sources inserted, right, some operator insertions at some point on the background, is equal to the partition function of quantum gravity on ADS, where we have to fix the boundary conditions of the quantum gravity path integral. So in quantum gravity, the geometry is dynamical, but the boundary conditions for the geometry are not. So in particular, we want to fix the conformal metric at asymptotic infinity. That corresponds to the background that we're computing the CFT on. So these match between the two sides. And we also have to fix the boundary conditions for the matter fields. Okay? And the boundary conditions for the matter fields are going to be dual to the sources that we inserted in the CFT path integral. So this tells us that for any partition function of the CFT, even ones with sources and so on, then there's an analogous computation in gravity that will give the same answer. Okay, so we're going to compute this ZADS, but we're going to compute it in a semi-classical approximation. So this is in principle a full gravitational path integral, but we don't really know what that means or how to do that. So we're going to treat it as a semi-classical computation where we have some set of possible saddle point geometries. So Z semi-classical with some fixed particular geometry G, okay? And then we're just going to look for the largest such semi-classical partition function such that it's a saddle point with respect to G, i.e. Z30 classical dG is equal to 0. Okay? So we're not going to attempt to integrate over all geometries. We're just going to look for a geometry that is going to solve the semi-classical equations of motion, and then we're going to do a semi-classical path integral in that fixed background geometry. Okay, so in particular, Z semi-classical of G is going to be equal to an integral over the matter fields, which we're treating fully quantum mechanically, of e to the minus just the Einstein-Hilbert action of G. Okay, so S Einstein-Hilbert minus the S matter of the fields phi in the background G. Okay, so because we fix G, then Einstein-Hilbert action is just some classical piece, but this is depending on the fields phi, which we're then going to integrate over. So they're still being treated quantum mechanically. Okay? Yep.
So my understanding is that the Euclidean path integral saddle point approximation works because we have like e to the minus something, and we take the minimum there of the something, and that's the biggest contribution.
Yep.
But I've heard that never actually checked, but I've heard that the Einstein-Hilbert action is unbounded from below.
Yep.
Why is this, is that still true with these boundary conditions? And if so, why do we expect this to give a reasonable at all?
This is still true. It's the so-called conformal mode problem. Basically, rescalings of the metric increase the Einstein-Hilbert action, like position-dependent ones, rather than decreasing it. So the usual story of how we'd want to make that well defined is just that we want to rotate the contour we integrate over by an imaginary part for those ones so that they decay rather than getting bigger. And you can worry about how well defined that is as a prescription. I think at the level of semi-classical saddle points, you can make something sensible where the integral around the saddle point converges. To try and make something sensible for the full path integral in higher than, say, 2 dimensions seems very hard, and we certainly don't know how to do it. But just for perturbations about saddle point, I think you can wick rotate all the modes that sort of grow as. The problem is modes like delta, call it delta x, right? That it looks like e to the delta x squared rather than e to the minus delta x squared. And if we change our integral so that rather than integrating over delta x from minus infinity to infinity or whatever, then we integrate it over it from that to that, then this becomes a convergent thing. So we just wick rotate the contour of integration to try and get it controlled.
But that seems like changing the formula for what...
Well, we don't know what the right... We don't know what we should be integrating over when we do the gravitational path integral, but it should be presumably something that is controlled. I agree. We don't... Okay, here's what I would say. We know that we have quantum field theory. This is the quantum field theory. We know that we have classical general relativity, that quantum matter back reacts in a semi-classical way. That's what this is doing. And this, that's what the d by dg is giving us. It's going to give us the semi-classical Einstein equations. So we know all this works. Where it comes from, we don't know. But just at an effective theory, like do what works level, then this seems to work for describing stuff in our universe. So we're going to try to use these rules to describe ADS.
Okay,
Okay.
Thanks.
Great. Yep.
So just make sure I'm correctly. Is this ZN symmetry from before coming from the fact that we were taking the trace and there's a cyclic symmetry in the trace?
Yep.
Okay.
Yep.
Second question is, it seems that now we're going to do some bulk computation.
Yep.
Do we know that this ZN symmetry stays in the bulk?
Great. So that is exactly what I'm now going to talk about. So we're really doing a path integral here when we write Zn. We're doing over these full n copies up here, right? But in practice, we can, because there's this symmetry, we can imagine we're doing a path integral over just one copy of the thing, just with these these n sheets of it, so that when you go around here, you end up on another sheet. Like there's an equivalent way to describe that particle just in terms of this one copy. Okay? We're going to make an assumption. This is the big trick Lukovitz, Maldacena made, that this Zn symmetry extends to the bulk. The dominant bulk saddle has Zn symmetry. There's really two parts to the assumption. One is that we only ever have to worry about one saddle when we're doing the full computation, or rather one family of saddles with respect to n that are going to be analytic in n, and each of those is going to have the Zn symmetry. Okay? So, if this is true, then the bulk saddle point geometry can be described as follows. Okay, so really what we have is some metric that are called G subscript n, that on the full n copy replicated geometry, but if that geometry has a Zn symmetry, then all that data can be equivalently described on the quotient of the full geometry by the Zn symmetry. So, in particular, we have some metric, G1, I've given n to indicate that it can be different for different n's. This is going to be just the metric on the quotient of geometry. Okay, so these are sort of equivalent. So if we look at some point in the bulk, sitting somewhere inside this sphere, okay, then the metric at that point is described by Gn, but it's also described by G1n, right, because it's the same, we have the same metric in the interior of this bulk, and we have the same metric in the interior of this bulk, and so on, and they're all, they're different points in the n-replicated geometry, but they have the same metric, and so we can describe all of those metrics by just a metric on the quotient of geometry on the one copy thing. Okay? But there's one more piece of data. This on its own is not enough to describe the full replicated geometry, because we need to specify where these branch cuts are in the bulk. Right? So on the boundary, if we want to describe the full n full cover, we need to describe the metric and the sources on this thing, and we need to say that there's a branch cut that extends through this region and through this region. And when you know both of those things, then you know what the full replicated geometry looks like, and you can go up to it. Okay? So we need some surface, gamma n, that describes the boundary of the branch cut in the bulk replicated, on the bulk quotient of geometry. So where you have to go, the equivalent of this little loop that will take you from one sheet to the other sheet. Okay? Because this bulk geometry has to match these boundary conditions here, then if we have some surface gamma, where near the boundary, the branch cut just has to become this branch cut big B, okay? So we necessarily have to have, at least in simple cases, that gamma union B gives the entire boundary of the branch cut, including the asymptotic boundary. So it has to be the boundary of some region little b that describes where there's the branch cut. So you go from one sheet to another. If you loop around gamma, and you go outside the branch cut, and then back through the branch cut through B. Okay? Through little b. Is that clear to everyone? So this is just extending into the bulk, this branch cut that has a boundary point here, and a region where the branch cut exists that was big B, and we want that to extend some distance into the bulk, and at some point it will end. It will end on some codimension 2 surface gamma. Okay? Okay. So I claim to you that specifying these two things is the same as specifying the full replicated geometry, for the same reason that specifying big B and the geometry of the single copy here was enough to describe that full n-fold cover over there. Okay? So that means we could have equivalently written ZADS as the max over G1n and gamma n such that delta Z semi-classical by delta G and delta z semi-classical by delta gamma n are both equal to 0. Okay, so we just, and here we have delta z semi-classical of the Gn that is described by those two things, so G1n, say G1n, and gamma n. Okay, so we've just said that if it's an extremum of Gn, it needs to equivalently be an extremum of these two things that describe the same data. Okay?
So is the branch cut in the bulk going to be codimension 1?
Sorry, say that again. So I need to get my terminology right. Branch cut on the boundary would be big B, which is codimension 1, and similarly the branch cut in the bulk is little b, which is also codimension 1. Though, where the branch, what's really well defined is the boundary of the branch cut, right? Because you can move the branch cut. If I moved B up a bit or down a bit, then it's still true that if I go in a loop around here and go back where I started with, then I end up one sheet over. So the really well-defined thing is the boundary of the branch cut and which side the branch cut is on, basically.
Oh, sorry, these are static. We're still analyzing.
Yeah.
Okay.
It's all Euclidean, so yeah.
And I'm a little uncomfortable with the ZADS equals maximum over those. Wouldn't it be more reasonable to do a sum?
Yeah, let's make it max extremum.
No, what I mean is if we're thinking about it like a sum over saddle point, like you know what I mean?
We want to be, it's a max over the saddle points. There's a discrete set of saddle points in general. So in general, there will be an actual maximum one.
But the path integral is the sum of geometries, and I'd expect it to be the sum of saddle points and the saddle point approximation, not the maximum saddle point.
Yeah, but the dominant contribution is going to come from the saddle point that gives the largest one. We're dropping everything except the dominant saddle point. Sorry,
okay.
Sum versus maximum. Yeah, that's another approximation we're making that will be, can lead to wrong answers sometimes, but it normally works, which is that we only have to worry about the leading saddle point.
Good. Okay. Thank you.
Okay. Okay, so we're starting to get somewhere now. So the key point is that we've now managed to rewrite this bulk replicated geometry saddle point approximation in terms of quantities, let's see, G1n and gamma n that don't obviously require us to have n be an integer, right? This is just some geometry on one copy of one single copy of the geometry, and this is just some surface in the geometry, and they depend on n in some way, but there's no obvious reason we're going to need n to be an integer. Okay, so if we can rewrite the whole calculation of z semi-classical in a way that doesn't explicitly depend on n being an integer, then we're going to be able to take n to be a non-integer, and we'll be able to take a derivative around n equals 1. Okay? So let's try to do this. Okay? So the first thing we want to do is we want to write the Einstein-Hilbert action in terms of G1n and gamma n. Okay? So the Einstein-Hilbert action is just the integral of dnx square root minus g of r on this full n-fold replicated geometry, okay, where this is gn and this depends on gn. Okay? So away from the branch cut gamma n, then gn and r of gn are just equal to g1n. Okay, they're just equal to the geometry on the quotient of geometry. Okay, so it almost looks like this is just n times the integral over the single copy geometry of the Einstein-Hilbert action with a metric g1n. But there's a subtlety that comes from the fact that we have this branch cut, right? So let's suppose some local point on gamma, because one of these geometries is going to be replicated, so you have to go around this surface n times to get back where you started, and one you only have to go around one time, at least one of them is going to have a conical singularity. Okay? Right? One of them is going to have a conical singularity with opening angle, what did I call it here, phi, and the other one's going to have a conical singularity with opening angle n phi. Okay? So in the quotient of geometry, in this integral, the contribution from that conical singularity is in fact n times the integral over gamma of the induced metric on gamma times phi minus 2 pi. And in fact, we had a, I think 1 over 16 pi g here. Just get the numbers in, and a 1 over 8 pi g here, it turns out. Okay? So that's the contribution we got from this thing, but what we wanted was the contribution from this thing. So we should subtract this off, and instead add in a single conical singularity with opening angle n phi, okay, rather than n conical singularities with opening angle phi. Okay, so this one is just almost the same thing, but it's 1 over 8 pi g, integral over gamma squared minus h, n phi minus 2 pi. Okay? Amazingly, the phi contribution here, the n phi here, and the n phi here cancel out, okay? But what doesn't cancel out is we have n times minus 2 pi here, whereas we only have minus 2 pi here, okay? So in fact, the Einstein-Hilbert action on the full replicated geometry is equal to the Einstein-Hilbert action on the quotient of geometry plus n minus 1 times 2 pi over 8 pi g times the integral over the surface gamma of its volume, so that is just the area of the surface gamma. Okay? Cancel out this 2 pi with the 1 over 8 pi g, and magically, we've ended up with something proportional to a over 4g. Okay? Sorry? Yeah, so the phi was the opening angle around this conical singularity at the branch cut in the quotiented geometry. And then in the replicated geometry, the opening angle around the conical singularity is n times phi. Okay? But then it ended up cancelling out, and we just ended up with something proportional to the area of the geometry. Okay. Yeah?
Could you explain that point again about how we, like, what's the prescription to dealing with these branch cuts? Is there a more visual way of seeing this? Because of these branch cuts, then I guess you'll have a singularity, like a conical singularity, when you stitch these up in the replicated.
I didn't tell you how to compute the action for the conical singularity, but it's just, you can treat it locally as like, it's literally a cone, and it's Minkowski space with the conical singularity, and you want to smear out the tip of the cone to make R well-defined, and then you just get an answer that's proportional to that. It's just a computation that can be done. I was just skipping to telling you the answer.
Okay, and
yeah, so the point is that if we had the quotient of geometry, and we didn't know anything about the fact that there's a branch cut there, then we would have, when we computed the action, we would have got a contribution, in a slightly smoothed out geometry, we'd have got a contribution that looks like just phi minus 2 pi times integrated over the surface. But the real contribution that we wanted was n phi minus 2 pi, and just one copy of it, because there's just, the point is that in the quotient of geometry, there's, if we just replicated the quotient of geometry n times with no branch cut, we would have n copies of this surface, each with opening angle phi. But in the real replicated geometry, we have one copy of this surface with opening angle n phi. Okay?
Thank you.
Okay. We're almost there, folks. It's a tough derivation, but it is rewarding. So, yeah. Okay, so the one remaining thing we need to deal with is this integral d phi of e to the minus s matter. Okay? Which we can just think of as z matter on the n-fold replicated geometry. Okay? But I already told you, way back at the beginning, I think it's probably got erased now, what the path integral of some matter thing over an n-fold replicated geometry is, right? Because we have z matter on the n-fold geometry over z1 to the n is just the trace of the density matrix of the matter on the region rho B, where the branch cut is, to the power n. Okay? So, that's just exactly the same thing as the boundary computation we did originally, but it's now interpretation in the bulk quantum field theory rather than the boundary theory. Okay? So let's move this across, and we have z1 to the n, trace of rho to the n. Okay. So now we're almost done, but now we just have to impose the conditions that we have a saddle point. So yeah, now this is defined when n's not equal to 1. This is defined when n's not equal to 1. This is defined when, this is defined when n's non-integer. This is defined when n's non-integer. We've now rewritten the whole bulk path integral, which only actually made sense for integer n when you had this replicated geometry, which is what we're trying to compute. We've rewritten it all in terms of things that only depend on n in some simple analytic ways. And so we can now just analytically continue n to anything we want and try to compute the answer. Okay? In particular, we're going to want to care about the case of n very close to 1 because that's what's going to compute the entanglement entropy for us. Okay? So we're now going to stick n equal to 1 plus epsilon and then take the limit where epsilon goes to 0. Okay? Okay, so first thing we want to do is, I don't know, I've lost my sheets of paper, whatever. Okay, we want to take the derivative with respect to the quotient of geometry of log of the semi-classical path integral on that geometry, okay, at n equal to 1. Okay, so at n equal to 1, this term is equal to 0, okay? This term is just the Einstein-Hilbert action on the quotient of geometry because there's just one copy of the quotient of geometry. This thing is just the matter partition function on one copy of the geometry, and this thing's just equal to 1 because it's just trace of rho, which is equal to 1, okay? So the only contributions that show up when n is equal to 1 are the derivative with respect to the metric of the Einstein-Hilbert action just on that n equals 1 geometry. That just gives us the Einstein term, 1 over 8 pi g times r mu nu minus a half g mu nu r. Okay, that's how we define Einstein's equations. And then we also have the derivative of log of z matter of 1 with respect to the geometry. Okay, the derivative of partition function with respect to the geometry just gives us the expectation of the energy momentum tensor in that geometry. Okay, so what does this tell us? It just tells us that the geometry G close to n equals 1 has to satisfy the semi-classical Einstein's equations, that the Einstein tensor has to be equal to 8 pi g times the expected energy momentum tensor of the matter. Okay? So that's great. That's telling us that close to n equals 1, the geometry is just the saddle point geometry at n equals 1. I guess that's obvious, but yeah. And the other thing we have to do is that we have to have the derivative with respect to the position of the branch cut be equal to 0. Okay. So let's say we just set n exactly equal to 1. We didn't have an epsilon here. Okay, we're going to take the limit where epsilon goes to 0. This term does not depend on where gamma is. Sorry, this term does not depend on where gamma is. It just depends on g. This term is proportional to n minus 1, so and n equals to 1, and then it's just 0. So that gives us 0. This thing does not depend on where gamma is. It's just a partition function on one copy. So that doesn't depend on gamma. This thing is just equal to 1, so that also doesn't depend on gamma. So we just have that at n equals 1, this is identically equal to 0. So setting it equal to 0 does not fix where gamma should be. Okay? So what does that tell us? It tells us to know where gamma is, we need to go one higher order in epsilon. We need to start looking at the order epsilon contributions to the action and see whether they fix gamma. Okay? So what are the order epsilon contributions to the action? Well, we have epsilon times a gamma over 4g. Okay? So we have epsilon, we have d by d gamma of epsilon times a gamma over 4g. Yeah, we also have epsilon times this thing, but that doesn't depend on gamma, so we'll forget about it. It will vanish when we take the derivative with respect to gamma. Again, this thing doesn't depend on gamma. And finally, we have this thing that does depend on gamma because it's the density matrix of little b. Okay, and little b is bounded by gamma. Okay, so when n close to 1, order epsilon, then this thing is just equal to 1 minus the trace of rho little b log rho little b. In other words, it's just 1 minus epsilon times the entropy of little b. Okay? So, yeah, so this should be minus this because this was in the action, and log z looks like minus the action. And this thing, so we then get minus epsilon times s of little b. Okay? Take the epsilons out the front, and this just tells us that gamma has to extremize the generalized entropy. Okay, that is exactly what we wanted for a quantum extremal surface. Okay, so almost done. We now know that close to n equals 1, the geometry G1n is just the ordinary geometry of the state psi, and gamma sits on a quantum extremal surface. So all that's left to do is to compute trace of rho to the n, which is just Zn over Z1 to the power n. Okay? And again, we'll notice a trick here, which is all the terms in Zn that scale linearly with n, okay, in log Zn that scale linearly with n, will just get cancelled by the denominator of Z1 to the power n. Right, so this term just exactly cancels out with the analogous term in Z1 to the n. Similarly, this Z1 to the n here of the matter exactly cancels out with the corresponding term in Z1 to the n. So the only terms we're left with are these two terms here, which we already computed to order epsilon. So we find that this is 1 minus epsilon a gamma over 4g plus s little b. Okay? There's a final step here, which is that we're told if there are multiple saddle points, we should take the one that gives the largest value of z, because that will be the dominant saddle point. So if there are multiple solutions gamma that are extremum of this thing, then we should take the one where this is smallest, because that will make this thing largest. Okay, so we've now got that we should take the quantum extremal surface, the saddle extremum of generalized entropy that has smallest generalized entropy, and then finally we have the s of b, which is equal to minus the derivative of this with respect to n, or equivalently with respect to epsilon, and so we just find that this is a over 4g plus s of b. Okay, so that was a long derivation. There's a load of steps to it, but I do think it's worth seeing in detail at least once in your life. But probably you've forgotten various details, so I just want to go over once more what the sort of essential points are. Everything else can be forgotten. Okay, the key trick is that we had some bulk path integral on these n copies of our system where n had to be an integer. But then we rewrote that bulk path integral in terms of variables gamma 1n and g1n that only involved one copy, and so there was no reason for n to have to be equal to 1. And in fact, that we found the partition function just depended on n in a simple analytic way. We just had some factors of n out the front of things and some geometries that depended on n. And then we took the limit where n goes to 1. At leading order, at n equals 1, the geometry was fixed to be the saddle point geometry of just n equal to 1, so there was no back reaction or anything. But the extremal surface was not fixed. But then we went to order epsilon. The extremal surface got fixed to be an extremal surface, to be extremum of generalized entropy. And we found that the only terms in Zn that didn't scale linearly with n in that expansion were just epsilon times the generalized entropy. Okay, and that's what finally got us the right answer. Okay, I don't know how long I have left. I think I'm sort of pushing. Can I get like 10 more minutes? Yeah, okay, great. So the final, after all that effort to derive this formula, I now just want to briefly point out to you guys that the QES formula is total nonsense. It doesn't make any sense at all. It's not even right to leading order in 1 over g. And all of that was completely pointless because sometimes it just gives totally nonsense answers. Obviously, that's some hyperbole. Normally, it gives excellent answers. But sometimes it does give nonsense answers, so we should at least know when it gives nonsense answers, so we know when to apply it, and we only apply it in circumstances it's actually going to give sensible things. Okay? So this was actually a paper I wrote with Chris, who's in the back there, in 2020. And it's a very simple setup to show that the QES prescription is nonsense. We're just going to consider a geometry in ADS3 with a load of very hot gas sitting in the middle. Okay? So this gas, if it was in a thermal state, has some entropy, which I'll call STH. And then we're going to consider the entanglement entropy of some region B consists of 2 regions on the boundary, and it's chosen such that the area of the surface that I'll call, I believe, A2. So A2 consists of this surface and this surface, and the surface that I'll call A1 that consists of those top 2 surfaces are very, very similar to each other. Okay, so this is almost exactly half the boundary. It's just near the transition point where this goes from being minimum to this being minimum. In particular, that's going to let us set things up so that we can have A1 over 4G be much bigger. And by this, I mean a much more than order 1 gap, larger than A2 over 4G, but still be much smaller than A2 over 4G plus the thermal entropy of all this hot gas in the middle. Okay, because I can make the thermal entropy be pretty large. I can't make it necessarily be order 1 over G, but I can make it be pretty big. I could also stick a black hole in the middle and then really get a big entropy if I wanted. It's just sort of nicer to not have to worry about a black hole. Ooh. Okay. Okay, now I'm going to consider calculate the entanglement entropy of 3 different states. The first is going to be a state I'll call rho thermal, where the hot gas is just going to be in an actual thermal state, in the canonical ensemble. Okay? So we want to work out what the quantum extremal surface is for this quantum computation. Sorry, I've done this wrong. I wanted to have B be down here and up here. Sorry about that. I wasn't looking at my own diagram. Okay. Yes? Sorry? Is there
If we are close to the tie, why is A1 much larger than A2 there?
So I tuned my region B so that this is true. Okay, because I'm just wanting to construct a counterexample to the quantum extremal surface prescription that is clearly nonsense. And so I can choose B to be whatever I want, and I've chosen it so that both of these things are simultaneously satisfied. So A1 or A2 are very close to each other, but A1 is slightly larger, and G is very small. So this one is much bigger than this one. But also we can still have this one be much bigger than this one because this thermal entropy can be very large if I have a load of hot gas. Yep.
If the bulk quantum fields give thermal entropy that's greater than order 1 over g, or like that order, is this still
it doesn't have to
semi-classical?
be greater than order 1 over g because I can tune my region big B to make the gap between A1 and A2 parametrically small. So we could also put a black hole in here and have it be order 1 over g, but I can also tune the region B to make it so everything works. So you can think of it as I take g to 0, I simultaneously take B to be almost exactly half the boundary.
Okay.
Okay. Okay. So because of the way I set things up, for SB of rho thermal, then the generalized entropy of this blue surface is just A1 over 4G. The generalized entropy of the white surface is A2 over 4G plus all the entropy of the bulk matter in the middle, so plus rho thermal. I set things up so that that was bigger than this. Okay, so the smallest one is this horizontal surface, and so the entropy of this is A1 over 4G. Okay, all great. I could also consider the generalized entropy of some pure state phi, where all this hot gas is just in some typical energy eigenstate or something like that. Okay? So now the generalized entropy of this is still A1 over 4G, but now the von Neumann entropy of this stuff is equal to 0. Okay, it still has thermodynamic entropy, but it doesn't have any von Neumann entropy. So the generalized entropy of the white surface is just A2 over 4G. So now that's the smaller one. So in this case, we have this is equal to A2 over 4G. Okay, and then the final state I'm going to consider is very simple. It's just going to be the state rho thermal with probability of half plus probability of half of being in the state psi. Okay, so this bulk state just has probability of half of being in some particular energy eigenstate and probability of half of being in any other random state in the canonical ensemble. Okay, this is just some pretty arbitrary seeming state, but I can compute it. And it has entropy. You know, the von Neumann entropy of the hot gas is now very close to half of the thermal entropy. Okay? So what does the QES prescription say? It says that the entropy on big B of this state rho is given by the smaller of the generalized entropy of the blue surface, which is basically just A1 over 4G, or the entropy of the white surface, which is A2 over 4G plus a half S thermal. Okay? So if I imagine, sort of shifting my region B so that the gap between A2 and A1 gets bigger or smaller, or I could imagine, in fact, yeah, okay, it's just given by the smaller of these two things. Okay? I claim to you that this formula is total nonsense, and in fact, I'm a bit short of time, so I'm not going to explain why, but it should hopefully be intuitive. Given that this state is just a 50-50, this state rho is just a 50-50 mixture of these two states, then SB of rho is always equal to a half A1 over 4G plus A2 over 4G plus at most order 1 qubit. Okay? This follows by, yeah, there's a couple of ways to derive this. I'll leave this in exercise. But you can consider the state a half rho thermal tensor 0, 0 on some reference system plus a half psi psi tensor 1, 1 on that reference system. And that state, the entanglement entropy, can be computed explicitly, and it's equal to this thing plus 1 qubit. Okay? But then when we trace out the reference system, that can only change the entropy by at most 1 qubit, and so we have that would tell us that this is true plus somewhere between 0 and 2 qubits. Turns out it's actually between 0 and 1, but don't worry about that. Okay, so this is just very basic quantum information, tells you that this has to be the case. It's the same reason that when we had a 50-50 mixture of the thermal state and a pure state in the bulk, then the entropy was just half the thermal state, right? Because there's a 50% probability it has that entropy. Okay. So, this is obviously nonsense. And yeah, the answer is that these two computations were correct using the QES prescription. This one was just not. So this formula will in general differ from this one by some arbitrarily large amount. Order the thermal entropy, order the differences between these two things. If we make this a black hole, we can actually make it order 1 over g. So it's a leading order breakdown. It's not some small correction. It's just totally spitting out nonsense. So I don't have time to in my paper with Chris, we talk about, like, you can actually see why the derivation that I gave before is breaking down. And basically, it's because you can't just assume there's a single Zn symmetric saddle. You have to include the effects of other saddles, including ones that break the Zn symmetry. And then you have to analytically continue that full sum of saddles, and it's a much more complicated procedure. But I just want to give you a sense of why you couldn't trust this computation, whereas you could trust these ones. And it's a very simple reason that in the bulk, we had a state that had one very, very big eigenvalue, namely like a half in this case, and then a load of really, really tiny eigenvalues, okay, e to the minus s thermal. In contrast, in these two states, all the eigenvalues in the bulk were roughly the same. In this one, it was just eigenvalue 1. These are the eigenvalues of the density matrix. Eigenvalue 1, and here they're e to the minus s thermal. Okay? In general, yeah, when you have large gaps like this, then you need to be very careful when to apply the QES prescription, and you can end up having sort of half the state wants to have this as its quantum extremal surface, and half the state wants to have this as its quantum extremal surface, and you get contributions from both of them at the same time. Okay? Yeah, go ahead with the question.
So earlier I asked about the maximum for the partition function. If you do instead of sum over saddles, does that sort of...
Yeah, so in general, you can't include the effects of all saddles. In simple circumstances, you can include the effects of a whole class of relevant saddles, or even potentially all saddles in like 2D or something. And when you do that, then you get the right answer.
Okay, cool. And so it's
it is exactly the question you were asking about why it broke down. Okay, so
can I ask a question?
Yep.
It's me? Sorry. Excuse me. I wanted to ask one thing.
Yep.
If sorry, I overlapped.
No, I was just looking around aimlessly.
I wanted.
Masks don't help.
Sorry.
No, it's all good.
I wanted to ask one thing, that if we consider the replica trick in CFT, what implements the Zn symmetry is the twist field. Did someone work out at something that is dual to a twist field in ADS? Because we are implementing Zn symmetry between ADS, but that surprised me a lot. It's the first time that I see something like that.
So the twist field is just a way of talking about the replicated geometry in terms of the unreplicated geometry. So you can think of the gravitational calculation as having a twist field at the surface gamma. Okay? Yeah. And then you're integrating over all positions where that twist field is inserted. But what it's really coming from is an integration over all geometries of the fully replicated geometry, and then just the fact that we happen to have a saddle point where that has that Zn symmetry. So the twist field is basically a mathematical thing. It's not something that you need to have as part of your theory or something like that. If what you're really interested in is the replicated question.
Okay, thank you.
Okay. So yeah, Chris and I had introduced this better version of the QES prescription that, roughly speaking, tells you when you can apply it and when you can't. When you can't, it turns out the right answer is just generally complicated and a mess. And to really describe that prescription properly, I'd need to take a lecture to define some tools from quantum information theory called one-shot quantum Shannon theory. But morally, what you need to have is you need to have the area of this surface, either the area of this surface plus the log of the largest eigenvalue minus the log of the largest eigenvalue of this thing is already, let me get this the right way around, is already larger than this one, or you need to have this one plus the log of the smallest eigenvalue minus the log of the smallest eigenvalue is already smaller than this one. So you need to have the same, if you replace the entropy of this stuff in the middle by either the largest eigenvalue, log of the largest eigenvalue, or the log of the smallest eigenvalue, it shouldn't change which of the two extremal surfaces is dominant, okay? If it can change which one is dominant, then you have a problem and the QAS prescription can't be applied. In fact, it's more complicated than that because in general you could have matter here, you could have matter here. All that matter could be entangled in some complicated way, but there are quantities that, morally speaking, generalize the log of the largest and smallest eigenvalues in a way that lets you define something sensible. Sensible conditions for when you can trust the QAS prescription. Yep.
Maybe this is naive, but couldn't you just characterize it as it only works for mixtures of states that are semi-classically connected to each other in some sense? Like perturbations around ADS are all valid contributions. If you have a black hole, you can't include that in the mixture.
So this is just some hot gas in ADS, and it's the same temperature hot gas for both the pure state and for the mixed state. So the geometry is really exactly the same. There might be a bit of back reaction, but it's the same for both of them. You really do have a fixed semi-classical geometry here, but you still have this problem. So it's really about the bulk quantum fields being in a weird state rather than about the geometry and superpositions of different geometries.
But you said the 1/g corrections come in when you turn the thing into a black hole. For example, I'm just talking about.
We can make them arbitrarily close to 1/g without having to have any black hole. Okay. Certainly, we can make them arbitrarily large compared to order 1, and the point of the QAS prescriptions is meant to get you the order 1 part. So yeah.
Thank you.
Okay. Yeah, I think I should end it here because we've I guess Andrea and I both ran over a bit, and so we're now a long way run over. We should go get some lunch. But tomorrow we will talk about go back to the evaporating black holes and see how these set of ideas from Lukowitz-Matassina and so on can be applied to derive things like the page curve just from gravity. Okay.
Thank you.
Cool.